Look at your hands. Solid, right? Touch the desk. It feels hard, real. This is the world we live in, a world of certainty, cause and effect. If you throw a ball, it arcs through the air and lands where physics says it should. We call this classical physics, the religion of Isaac Newton. For 300 years, it was the unshakable truth. It put men on the moon and predicted the orbit of planets billions of miles away. We were the masters of the machine. But there was a crack in the foundation. A tiny, almost arrogant assumption. What if I told you that the ball, on its journey through the air, didn't actually exist? What if it was everywhere at once? What if the act of you looking at it forced it to choose a location? Welcome to the jungle of the quantum. A place where the rules of reality are written in sand, where the universe is not a machine, but a ghost story. My name is the narrator, and tonight, I'm going to show you why the greatest minds of history were driven to the edge of madness. This is the story of the quantum, and it begins with a lie. In the late 19th century, physicists were bored. They believed the work was done. They had figured out the universe. Lord Kelvin, one of the most brilliant men of the era, famously declared, "There is nothing new to be discovered in physics now." It was a matter of polishing the details. But nature had a cruel joke waiting. And it was hiding in the most mundane of places: heat. Specifically, the ultraviolet catastrophe. When scientists tried to calculate how much energy a hot object, like a light bulb, should emit, the math went insane. It predicted that it would emit an infinite amount of energy in the ultraviolet range. It was a mathematical apocalypse. The numbers didn't lie, but they also couldn't be real. Enter a man named Max Planck. He wasn't trying to start a revolution. He was just trying to fix the math. He made a desperate bet. What if energy isn't continuous? What if it comes in small chunks? Like a cash machine only spitting out specific bill denominations. He called them quanta. It was a fudge factor, a dirty trick to make the equation work. He didn't even believe it. He just wanted it to be a temporary solution. But by thinking of energy as discrete packets, he had just shattered the bedrock of physics. Planck was a conservative. He wasn't trying to overthrow Newton. He was just trying to reconcile the math. The irony is that he lit the fuse on the most radical revolution in human thought, and he spent the rest of his life trying to put it out. To understand the madness of quantum physics, we have to understand the ancient war between light and matter. For centuries, we thought light was a wave, like ripples on a pond. It bends, it diffracts, it interferes with itself. This was proven conclusively by Thomas Young's famous double-slit experiment in 1801. Case closed. Light is a wave. Then came Albert Einstein in 1905. He was not the white-haired sage we see on t-shirts. He was a young, hungry patent clerk. He looked at the photoelectric effect. Why does light knock electrons out of metal? And declared the impossible. He said, light is a particle. He called them photons. This was heresy. How could light be both? A particle is a hard, localized object. A wave is a spread-out disturbance. This was the birth of wave-particle duality, the first existential crisis of the 20th century. The universe was playing games with us. It refused to be put into a tidy box. Was it a wave? Was it a particle? The answer was, it depended on how you looked at it. It's like asking a chameleon, are you green or are you brown? The answer depends on where you put it. Nature doesn't have to conform to our expectations. We just have to accept that we live in a universe that is fundamentally ambiguous. By the 1920s, we had a new model of the atom, courtesy of Niels Bohr. It looked like a tiny solar system. Electrons orbited the nucleus, held by electromagnetic attraction, just like planets held by gravity. It was beautiful, it was simple, it was wrong. According to classical physics, the rules of Maxwell and Newton, a spinning electron orbiting a nucleus should radiate energy. It should spiral into the nucleus and crash. The entire atom should collapse in a fraction of a second. So why are we here? Bohr, like Planck, used a quantum leap of desperation. He said that electrons don't orbit in a continuous spiral. They exist in fixed, quantized orbits. They don't exist in the space between them. They jump from one orbit to another without traversing the space in between. Imagine you're walking up the stairs in the dark. You don't exist on the staircase itself, only on the individual steps. You teleport from step to step. This was a radical idea that defied all logic. But even this broken model was a breakthrough. It explained why atoms emitted specific colors of light. Each jump down emitted a specific photon of energy, a specific color. It was progress. But it was about to get a whole lot weirder. The 1920s and 30s were the Wild West of science. The greatest minds in history assembled in Europe, primarily Copenhagen, to tear the universe apart and rebuild it. There was Niels Bohr, the oracle, the father of the Copenhagen interpretation. He believed that the quantum world was a different reality, one we couldn't understand with common sense. If you didn't like it, tough. There was Werner Heisenberg, the young Turk, a prodigy who would shatter the very concept of cause and effect. There was Erwin Schrödinger, the romantic, an Austrian genius who saw beauty in equations and hated the abstract nihilism of his peers. And there was Albert Einstein, the old guard, the rebel who had started it all, now found himself the conservative, refusing to accept the chaos he had helped unleash. He famously declared, "God does not play dice." This wasn't a polite academic debate. This was a war. They argued late into the night, often taking walks in the woods around Copenhagen. They argued about the nature of reality itself. Is there a real world out there when we aren't looking? And it was in this cauldron of genius and frustration that Heisenberg would drop the bomb. Werner Heisenberg was trying to build a new physics. He was working with matrices, complex blocks of numbers that describe the state of a particle. He realized something terrifying. You cannot know everything. He developed the Heisenberg Uncertainty Principle. It's not about the limits of our equipment. It's a fundamental law of the universe. If you want to know exactly where a particle is, its position, you have to hit it with a photon of light. But that photon pushes the particle, changing its speed, its momentum. Conversely, if you want to know exactly how fast it's moving, momentum, you have to let it be free, which means you lose track of its location. The more precisely you measure one, the less precisely you know the other. The equation is delta x times delta p is greater than or equal to h divided by 4 pi. This is not just a limit, it's a rule. It means that at its core, nature is uncertain. It implies that the future is not predetermined. The particle itself doesn't know where it is going. People often misunderstand the uncertainty principle as a measurement problem. It isn't. It is an ontological issue. It tells us that particles just don't have definite positions and momenta at the same time. That is not how reality is structured. It's a fuzzy, probabilistic fog. This was the first real punch to the gut of classical realism. The universe wasn't just fuzzy, it was fundamentally random. Einstein was horrified. God does not play dice, he insisted. But Heisenberg had the math, Bohr had the philosophy, and they were winning. The ghost in the machine. While Heisenberg was busy smashing the table of reality, Erwin Schrödinger was sitting in the Swiss Alps, perhaps recovering from a cold, or perhaps with a mistress. History is murky, but the result was clear. He invented wave mechanics. Instead of the clunky, abstract matrices of Heisenberg, Schrödinger treated the electron as a wave. He created a beautiful equation, the Schrödinger equation, that described the wave function of a particle. It was elegant. It was continuous. It made sense. He thought he had won. He believed he had restored order to the universe. But his equation had a monstrous implication. His wave wasn't a physical wave in water or sound. It was a probability wave. The amplitude of the wave at any given point represented the probability of finding the particle there. This means the electron isn't a point moving through space. It is a cloud of possibility. It is in many places at once, until you look. This was the birth of the Copenhagen interpretation, the standard view of quantum mechanics that still dominates today. It says that a particle is described by a wave function. The wave function is a set of probabilities. The particle exists in all possible states simultaneously, and observation collapses the wave function into a single, real outcome. The act of you looking forces the universe to make a decision. Erwin Schrödinger was horrified by the Copenhagen interpretation. He hated the idea that consciousness, mere observation, could affect the physical reality. So, he decided to destroy Bohr and Heisenberg with logic, by inventing the most famous thought experiment in history, Schrödinger's cat. Imagine we put a cat in a sealed steel box. Inside, there is a mechanism. There is a tiny bit of radioactive material. It has a 50% chance of decaying in an hour. If the radioactive atom decays, a Geiger counter clicks. The click triggers a hammer. The hammer smashes a vial of cyanide gas. The cat dies. If the atom doesn't decay, nothing happens. The cat lives. According to the Copenhagen interpretation, until we open the box, the atom exists in a superposition of decayed and not decayed. Therefore, the cat, via quantum entanglement, exists in a superposition of alive and dead. The cat is neither alive nor dead. It is a ghost. It exists in a state of quantum limbo. Only when we open the box, the observation, does reality snap into focus, and the cat is either alive or it is dead. This is the central paradox of quantum mechanics. It implies that at the macroscopic scale, our scale, reality is an illusion. It doesn't exist until it is observed. Schrödinger proposed this to mock Bohr. He thought it was absurd. But physicists today realize that, mathematically, it's exactly what the equations predict. Schrödinger wanted to save the cat. He wanted common sense to win. But the universe is not common sense. The cat, it seems, is always both, until it isn't. If you thought superposition was weird, hold on to your seat. We are about to break reality. In the 1930s, Einstein, Podolsky, and Rosen published a paper, the EPR paradox, designed to kill quantum mechanics once and for all. They argued, imagine you have two particles that interact and then fly apart. They are entangled. According to quantum mechanics, they still share a single wave function. If you measure the spin of particle A and find it to be spin up, then immediately particle B, no matter how far away it is, must be spin down. This is required by the law of conservation of momentum. But here is the kicker. This happens instantly. It doesn't matter if they are on opposite sides of the universe. The information isn't traveling, it's just a fact. Einstein called this spooky action at a distance. He said this proved quantum mechanics was incomplete. There must be hidden variables that we haven't discovered yet, some underlying rule that keeps the particles connected without needing weird voodoo magic. Einstein was wrong. In 1964, a brilliant physicist named John Stuart Bell developed a theorem that would settle the debate. Bell's inequality. He proved mathematically that if hidden variables existed, if the particles had a predetermined state before measurement, then there was a limit to how often certain correlations could happen. If quantum mechanics was right, the correlations would exceed that limit. It would prove that the particles are truly entangled, that the universe is fundamentally non-local. In 1982, Alain Aspect ran the experiment. He fired entangled photons through a complex system of detectors. The results were clear. Bell's inequality was violated. The universe is, in fact, non-local. The particles are not communicating via signals. They are one thing. They are part of a single, indivisible reality that transcends space and time. This means that the universe is a tapestry. You cannot cut a thread and pretend it doesn't affect the whole garment. The implications are staggering. If two particles can be connected across the universe, it suggests that everything is connected. It suggests that the separation we perceive between ourselves, the stars, the galaxies, is an illusion. We are all part of one big quantum system. We are ghosts in a machine that we don't understand. So, we come back to the observer. Quantum mechanics requires an observer to collapse the wave function. But what is an observer? Does it require a consciousness? A human mind? Does the universe only exist because we are here to look at it? Many physicists argue that an observer doesn't need to be conscious. It could be a particle interacting with another particle. The environment itself acts as an observer, decohering the wave function and collapsing it into a classical reality. But this doesn't answer the deeper question. Why does a single, solid reality emerge from a sea of probabilities? We are still the cat in the box, the holographic God. We are on a planet. The planet is orbiting a star. The star is one of billions in a galaxy. The galaxy is one of trillions in the observable universe. Our classical physics works perfectly for this scale. It gets rockets to Mars and satellites to Saturn. But 95% of the universe is missing. We call it dark matter and dark energy. We don't know what it is. We just see its gravitational effects on the stuff we can see. Classical physics falls apart here. Quantum physics might hold the key. Many physicists believe that quantum mechanics is the fundamental code of reality. Gravity is the last holdout. It doesn't play nice with quantum mechanics. Yet. If we can unify general relativity, gravity, with quantum mechanics, we will have the theory of everything. We will have the source code of the simulation. We have been discussing the Copenhagen interpretation, where the wave function collapses and one reality is chosen. But what if it doesn't collapse? Enter Hugh Everett and the many worlds interpretation. Everett argued that the universe doesn't choose. When you open the box, the universe splits. In universe A, the cat is alive. In universe B, the cat is dead. Both are equally real. The wave function didn't collapse. Your consciousness just became entangled with one branch of reality. Every time a quantum event occurs, which is billions of times a second, the universe branches. In one universe, you married your high school sweetheart. In another, you are the CEO of a tech giant. In another, you are no longer alive. The universe isn't a single story. It's a library of infinite stories. The many worlds interpretation is the only interpretation that takes quantum mechanics seriously without adding ad hoc assumptions. It says the wave function is real and it doesn't disappear. It just keeps going. It's not that we don't see other realities. It's that we are separated from them by a lack of interference. Is this comforting? Or terrifying? It means that everything that can happen does happen. Somewhere. This is the ultimate expression of quantum probability. Let's take the weirdness a step further. In the 1990s, physicist Gerard 't Hooft and Leonard Susskind proposed a radical idea based on black hole thermodynamics, the holographic principle. The math suggests that all the information contained in a three-dimensional volume of space can be encoded on a two-dimensional surface, like a hologram. A three-dimensional image is encoded on a flat film. If this is true, then our three-dimensional universe, the planets, the stars, us, might just be a projection of information stored on the boundary of the universe. Are we living in a cosmic video game? Is the spooky action at a distance simply a result of the fact that particles aren't really separate in the two-dimensional source code? This leads us to the ultimate conclusion. The universe is made of information. If quantum physics shows us that the universe is discrete, quantized, and probabilistic, and that observation defines reality, it looks an awful lot like a computer program. The simulation argument suggests that if a civilization can reach a post-human stage with immense computing power, they would likely run ancestor simulations, simulations of their own history. If that is the case, the number of simulated realities vastly outnumbers the base reality. Therefore, statistically, we are almost certainly living in one of those simulations. Consider this. The speed of light is the processing speed of the universe. Quantum uncertainty is the render distance to save computing power. Wave function collapse is the optimization of the rendering. Are we just ghosts inside a quantum machine? Elon Musk famously stated that there is a 1,000,000,000 chance we're living in base reality. It fits the data. It explains the strangeness. But it doesn't make us feel any more real. So, where does this leave us? We started with the lie of classical physics. We moved through the madness of the atom, the terror of the cat, the spookiness of entanglement, and the implications of the hologram. We are faced with a choice. There is the nihilist's view. Nothing is real. We are a random fluke in a meaningless quantum foam. It doesn't matter. Then there is the mystic's view. Everything is consciousness. We are the universe observing itself. Our minds are the interface that creates reality. Regardless of the math, you are here. You are experiencing this. The sunrise is warm, the coffee is hot. Quantum physics might tell us that the atoms in our coffee are just a cloud of probability, but the experience of drinking it is undeniably real. We do not know the answer, but the quest itself is the definition of humanity. We are the universe trying to understand itself. We are the observers, the creators, and the observed. The ghost in the machine has finally realized it is a ghost, but it still wants to know who wrote the code. I am the narrator, and this has been a night tale. Remember, reality is just a word for a dream we haven't woken up from yet. The ghost in the machine. We ended the first part with a smoking gun. The atom was a lie. Certainty was a lie. Heisenberg had proven that the universe doesn't know where it is going, and Niels Bohr was celebrating the death of causality. But the war was far from over. In fact, it was just entering its most brutal phase. While Werner Heisenberg was busy shattering the very concept of reality with his abstract blocks of mathematics, his matrices that seemed to have no physical meaning, a different kind of genius was sitting in the Swiss Alps. His name was Erwin Schrödinger. He was a romantic, a poet trapped in a physicist's body, and he despised the nihilistic fog that the Copenhagen school was spreading across Europe. He looked at Heisenberg's work and saw ugliness. He saw clunky, disjointed numbers that insulted the beauty of nature. So, Schrödinger decided to fight fire with beauty. He took the old, comforting idea of a wave, something continuous, something smooth, something predictable, and he created a masterpiece. He invented wave mechanics. The equation he wrote on that chalkboard in 1926 is now carved into the walls of physics history. It is called the Schrödinger equation, and it is one of the most elegant pieces of mathematics ever conceived. It describes something called the wave function. To Schrödinger, this wave function was the physical reality of the particle. It was a real wave, rippling through space like an ocean swell. It was continuous. It was deterministic. He thought he had won. He believed he had restored order to the universe. But then came the interpretation. Other physicists, particularly Max Born, looked at Schrödinger's beautiful waves and realized something terrifying. This wave wasn't a physical wave of matter like sound or water. It was a probability wave. The amplitude of the wave at any given point represented the probability of finding the particle there if you looked for it. Suddenly, the electron wasn't a hard little ball spinning around the nucleus. It wasn't even a physical wave. It was a ghost. It was a cloud of mathematical possibility. It existed in many places simultaneously. According to the math, the electron is not just likely to be somewhere, it is everywhere the wave spreads, until something happens to stop it. This was the birth of the Copenhagen interpretation, the standard view of quantum mechanics that still haunts physics classrooms today. It established three radical rules. First, a particle is described by a wave function, a mathematical ghost. Second, this wave function represents a set of probabilities, not physical realities. Third, and this is the kicker, the particle exists in all possible states at the same time. This is called superposition. And finally, observation collapses this ghost into a single, solid, real outcome. Let that sink in for a moment. The act of you looking forces the universe to make a decision. Before you look, the universe is indecisive. It's a fog of infinite possibilities. The moment you open your eyes, the fog disappears, and reality snaps into focus. This implies that the moon, as the famous physicist John Wheeler once put it, might not exist when you aren't looking at it. It sounds like the ranting of a madman, but mathematically, it was the cleanest explanation available. Erwin Schrödinger, the man who started this nightmare with his beautiful equation, was absolutely horrified by this interpretation. He hated it. He despised the idea that a conscious mind, mere observation, could dictate the physical state of the universe. He considered it philosophical garbage. He decided he would use logic to destroy Niels Bohr and his Copenhagen cronies. He would show them how absurd their ideas were by stretching their logic to the macroscopic world. He would create a monster. That monster is the most famous cat in history, Schrödinger's cat. Imagine a sealed steel box, dark and soundproof. Inside the box, we place a living cat. Alongside the cat, we place a fiendish mechanism. There is a tiny speck of radioactive material, just a single atom. There is a 50% chance that this atom will decay in the span of 1 hour. There is a 50% chance it will remain stable. If the atom decays, a Geiger counter detects the radiation, clicks, and triggers a hammer. The hammer falls and smashes a glass vial of hydrocyanic acid, which is a fast-acting poison. The cat dies. If the atom does not decay, the Geiger counter remains silent, the hammer stays suspended, the vial remains intact, and the cat lives. Now, here is the trap. According to the Copenhagen interpretation, the wave function of the atom does not decide to be decayed or not decayed until an observation takes place. It remains in a superposition of both states simultaneously. But the fate of the cat is directly entangled with the fate of the atom. If the atom is both, then the cat must also be both. Schrödinger declared that According to quantum mechanics, the cat is neither alive nor dead until we open the box. It is a ghost. It exists in a quantum limbo of life and death, rotating in a nightmare dimension of probability. He presented this thought experiment in a 1935 paper, intending it to be a devastating reductio ad absurdum. He was essentially saying, "Look, Bohr, look at the nonsense your philosophy leads to. The universe cannot possibly work this way. Common sense dictates the cat is either alive or dead, regardless of whether we look." It was a brilliant attack. But history has a wicked sense of irony. Today, most physicists will tell you that Schrödinger was wrong to mock it. Mathematically, the Copenhagen interpretation predicts the superposition of the cat. It is only the process of decoherence, the interaction with the environment, that forces one reality to dominate. But does the cat truly exist in two states at once, even for a moment? The mathematics says yes. The mathematics says the universe really is that insane. Schrödinger wanted to save the cat. He wanted to save objective reality. But the universe does not care about what we want. The cat, it seems, is always both alive and dead, until it isn't. But Schrödinger's cat was just the appetizer. If you thought superposition was weird, hold on to your seat. We are about to break the chains of space and time itself. We are about to enter the realm of quantum entanglement, a phenomenon so disturbing that Albert Einstein refused to believe in it for the rest of his life. In the same year as Schrödinger's cat, 1935, Einstein teamed up with two colleagues, Boris Podolsky and Nathan Rosen. They published a paper that would become known as the EPR paradox. The goal was to deliver a knockout punch to quantum mechanics. They wanted to prove that it was incomplete, that there had to be some hidden variables beneath the surface that we just couldn't see yet. Here is the thought experiment they devised. Imagine we have a single particle that through some quantum interaction decays into two smaller particles. Let's call them particle A and particle B. These two particles fly off in opposite directions. They go far away, maybe light years apart. However, according to quantum mechanics, they remain entangled. This means they share a single wave function. They are, in a very real mathematical sense, still one object. They haven't fully separated. Now, consider a property called spin. A particle can be spin up or spin down. Because of the law of conservation of angular momentum, the spins of these two entangled particles must be opposite. If particle A is measured and found to be spin up, then particle B instantly must be spin down. But here is the part that infuriated Einstein. Let's say particle A is in your laboratory on Earth. Particle B is in a spaceship on the other side of the Milky Way galaxy. You measure particle A, and it turns out to be spin up. The moment you get that result, you immediately know that particle B, trillions of miles away, is spin down. But how could particle B know? How could a piece of information travel across the entire galaxy faster than the speed of light? According to Einstein's own theory of relativity, nothing can travel faster than light. Information cannot be transmitted at superluminal speeds. Einstein called this spooky action at a distance. He was using a derogatory term, spooky, to mock the absurdity of it all. He argued that this proved quantum mechanics was incomplete. There must be hidden variables, some underlying instruction set that the particles carried with them at the moment of their creation. Like a pair of socks. If you put a left sock in one box and a right sock in another, and send them to opposite ends of the universe, opening one box and seeing a left sock immediately tells you the other box contains a right sock. There was no spooky action. The socks were defined from the start. Einstein believed this was the only logical explanation. He believed in local realism, the idea that objects have definite properties independent of observation, and that objects are only influenced by their immediate surroundings. He felt that quantum mechanics must be missing a piece of the puzzle. He spent the final decades of his life trying to find a way to complete it. But Einstein was wrong. In 1964, a quiet and brilliant physicist from Northern Ireland named John Stuart Bell decided to settle the debate once and for all. He developed a theorem that would change the course of physics. He derived what is now known as Bell's inequality. Bell's inequality is essentially a mathematical limit. It says, if the universe is locally realistic, if Einstein is right and particles carry hidden variables that determine their state before measurement, then there is a strict upper limit to how often certain correlations can occur between entangled particles. Let me try to simplify this. Imagine you have a machine that shoots out two coins. If you use a special filter to measure them, you find certain patterns of heads and tails. Bell proved mathematically that if the coins were pre-programmed, local realism, the patterns would never exceed a specific statistical threshold. However, if quantum mechanics was right, if the coins truly do not decide their state until the moment of measurement, if they are entangled, then the patterns would exceed that threshold. They would violate the inequality. It was a brilliant, elegant piece of logic. But for 20 years, it remained a purely theoretical debate. The technology to test Bell's inequality didn't exist yet. It required lasers, ultra-fast switches, and detectors that could catch individual photons before they had a chance to communicate with each other. Then came 1982. A French physicist named Alain Aspect ran the experiment. He built an intricate apparatus that fired entangled photons in opposite directions. He placed detectors far apart and switched the polarizers so fast that there was literally no time, not even a fraction of a second, for a signal traveling at the speed of light to pass between the two particles and tell them how to behave. The results came in, the data was printed out, and it was devastating. Bell's inequality was violated. The limit was broken. The universe is, in fact, non-local. Aspect's experiment proved that the particles are not communicating via signals. They are not sending secret coded messages to each other. They are simply one thing. They are part of a single, indivisible quantum system that transcends space and time. The concept of space itself does not apply to them. They are, as the physicist David Bohm called it, undivided wholeness. This means that the universe is a tapestry. You cannot cut a single thread in one corner of the tapestry and pretend it doesn't affect the pattern at the other end. The separation you see between yourself and the stars, between you and a particle on the other side of the galaxy, is an illusion. The universe is a hologram of interconnected information. The implications are staggering. If two particles can be connected across the universe, it suggests that everything is connected. It suggests that the individuality we cherish, this feeling of being a separate self, is a macroscopic illusion cooked up by our brains. At the most fundamental level, there are no individuals. There is only the quantum field. We are not just stardust. We are the universe looking at itself in a mirror. But the story doesn't end with Aspect. It gets even stranger. In 1999, a scientist named Marlon Scully took the EPR paradox and the quantum eraser concept and turned it into a nightmare for our understanding of time. He designed the delayed choice quantum eraser. The setup is complex, but the result is terrifying. In this experiment, a photon passes through a double slit. We can choose to observe which slit it went through. If we observe it, the wave function collapses, and we see a particle pattern on the screen. If we don't observe it, we see a wave interference pattern. So far, so simple. But Scully added a twist. He entangled the photon with another photon. Instead of measuring the original photon, he decided to measure its twin. He observed the twin photon to determine the which path information of the original photon. The original photon hit the screen, and then, moments later, he measured the twin photon. Here is the kicker. If he chose to measure the twin photon and keep the which path information, the original photon's pattern on the screen was a particle pattern. But if he chose to erase that information, to destroy the data, then the original photon's pattern on the screen was a wave pattern. The implication is that the experimenter's decision to measure or erase the information after the photon hit the screen determined how the photon behaved before it hit the screen. The future decided the past. The observer's choice retroactively collapsed the wave function. This is the quantum eraser experiment. It proves that cause and effect are not absolute. It proves that the arrow of time might be an illusion. The universe is not a sequential narrative of events happening one after the other. It is a block of information where the past, present, and future are intertwined. The ghost in the machine isn't just playing tricks on space, it's playing tricks on time itself. So, we are left with the observer. Quantum mechanics requires an observer to collapse the wave function. But what exactly is an observer? Does it require a conscious mind, a human soul, a beating heart? This is the most contentious question in all of physics. Niels Bohr famously argued that the observer doesn't need to be a person. He believed that a measurement could be made by any macroscopic object, like a Geiger counter. The act of the particle interacting with the physical apparatus is enough to collapse the wave function. But this is a cop-out, because a Geiger counter is made of atoms. Those atoms are governed by quantum mechanics. So how can a system of quantum particles collapse the wave function of another quantum particle? If you push the logic down, eventually you are left with a paradox. It seems that the collapse must happen at the interface between the quantum world and the classical world. But where is that interface? This led to the controversial von Neumann-Wigner interpretation, which suggests that consciousness is absolutely necessary for reality. The idea is that the wave function collapses only in the mind of an observer. The universe is a massive sea of superpositions, and our consciousness acts as a filter, picking one reality out of the infinite possibilities. This brings us dangerously close to mysticism. It suggests that without consciousness, the universe exists only as a dim, undefined blur. Many physicists despise this idea. They argue that it is arrogant to think that human consciousness is so special. They turn to the concept of decoherence. Decoherence is a process where a quantum particle interacts with its environment, the air, the light, the heat, and this interaction leaks the quantum information into the surroundings. To an outside observer, the particle appears to have collapsed into a single state, but in reality, the particle is just entangled with trillions of other particles. The superposition never really collapses. It just becomes so complex that we lose track of it. But even decoherence doesn't answer the fundamental question. It explains why we don't see superpositions in everyday life. But it doesn't explain the existential terror of the EPR paradox. It doesn't explain why we experience a single, solid reality from a universe made of probability waves. Let's look at the math. In physics, we use the density matrix to describe the state of a system. When decoherence happens, the off-diagonal terms of the matrix vanish. The math looks exactly like a wave function collapse. But is it really a collapse? Or are we just ignorant of the exact state of the environment? This brings us to a new interpretation called cubism, or quantum Bayesianism. Cubists argue that the wave function is not a real thing in the world. It is a statement about an observer's personal beliefs. It is a probability distribution, like the odds of a horse winning a race. When you observe the horse, the odds collapse. But the horse was always one thing. Cubists claim that quantum mechanics doesn't tell us about the universe. It tells us about our own ignorance. This is a practical way to avoid the metaphysical nightmare. But for those of us who are not comfortable with solipsism, it doesn't solve the problem. Because if the wave function is just a belief, then what is the universe actually made of? We are back to square one. The year is 2024, and we are still the cat in the box. We are still wondering if the moon exists when we aren't looking. We have built quantum computers that exploit superposition and entanglement. We have sent entangled photons into space. We have proven that the universe is fundamentally random. We have proven that the universe is non-local. We have proven that the future can affect the past. And yet, we still wake up in the morning, drink our coffee, and trust that the floor will hold us. We trust that the sun will rise. We trust that reality is solid. But it isn't. The universe is a ghost. It is a projection, a hallucination, a waking dream. We are not just living in the machine. We are the machine. And we are still trying to figure out where the electricity is coming from. The ghost in the machine has finally realized that it is a ghost. But it still doesn't know who wrote the code. And that, perhaps, is the most terrifying part of all. We are moving into the final frontier, where physics meets metaphysics, and we are about to ask the question that no one can answer. Is the universe real, or is it just a story we are telling ourselves? The answer, as we shall see in part 3, might be written on the edge of a black hole. The holographic God. We are on a planet. The planet is orbiting a star. The star is one of billions in a galaxy. And that galaxy is just one of trillions in the observable universe. It is a breathtaking hierarchy of size and scale, a cosmic ladder that stretches from the infinitesimal to the infinite. Our classical physics, the rules of Newton and Einstein, works perfectly for this scale. It gets rockets to Mars and satellites to Saturn. It predicts eclipses and guides GPS satellites with atomic precision. We are masters of the visible universe. But here is the cruel joke. Everything we see, every star, every planet, every swirling nebula, and every speck of cosmic dust accounts for less than 5% of the total mass-energy budget of the cosmos. 95% of the universe is missing. We call it dark matter and dark energy. We don't know what they are. We have never seen them. We have never touched them. We just see their gravitational effects on the stuff we can see. Dark matter acts like an invisible scaffolding holding galaxies together. Without it, they would spin apart and scatter into the void. Dark energy acts like an anti-gravity pressure, pushing the fabric of space-time apart faster and faster, tearing the universe at its seams. But classical physics falls apart here. The math breaks down. The theories explode into infinities. We are blind to the majority of reality. Quantum physics, however, might hold the key. Many physicists believe that quantum mechanics is not just a quirky set of rules for the tiny world. It is the fundamental source code of reality. It is the operating system upon which the entire universe runs. But there is a problem, a massive, gaping wound in the heart of physics. Gravity does not play nice with quantum mechanics. General relativity, Einstein's masterpiece, describes gravity as the curvature of space-time. It is smooth, continuous, and geometric. Quantum mechanics describes the universe as granular, probabilistic, and discrete. When you try to combine them, when you try to calculate the gravity of a particle at the quantum scale, the equations go haywire. They produce infinite answers. The universe, it seems, hates the union of these two giants. This is the holy grail of modern physics, the theory of everything. A single mathematical framework that unifies the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. If we can crack this code, we will have the source code of the simulation. We will know exactly what the universe is made of. Several contenders have stepped into the ring. The most famous is string theory. This radical idea suggests that particles are not point-like dots. They are tiny, vibrating strings of energy. The vibrations of these strings determine the properties of the particles: mass, charge, spin. To make the math work, string theory requires extra dimensions. We live in 3 dimensions of space and 1 of time, but string theory says there are 10 or 11 or perhaps 26 spatial dimensions curled up so tightly that we cannot see them. It is a beautiful, elegant, mathematically consistent idea. The problem is that we cannot test it. The energy required to see these strings is trillions of times greater than our most powerful particle accelerators. String theory has become a mathematical fantasy, a cathedral of ideas with no foundation in experiment. Another contender is loop quantum gravity. Instead of treating space-time as a continuous sheet, this theory suggests that space-time itself is quantized. It is made of tiny, indivisible loops, like the pixels on a screen. The universe is literally a grid. If you zoom in far enough, the smooth fabric of reality dissolves into a chunky digital foam. This theory avoids the extra dimensions of string theory, but it too struggles to make testable predictions. So, we are stuck. We have 2 brilliant, mathematically rigorous theories that describe reality, and they refuse to speak to each other. It is as if we have 2 maps of the same city, but one map shows the city built of marble blocks, and the other shows it painted on a canvas. They cannot both be right in their current forms. The truth must be something else, something stranger. This brings us to the first of the great existential questions in our search for the holographic God. What if the wave function doesn't collapse at all? We spent the entirety of part 2 assuming that the Copenhagen interpretation, where observation forces a single reality, was the standard. But what if it is a lie? What if the universe never chooses? What if every possibility that exists in the quantum realm actually happens, but just in different realities? This is the many worlds interpretation, first proposed by a brilliant and tragically underappreciated physicist named Hugh Everett in 1957. Everett was a student of John Wheeler, and he wrote a doctoral thesis that shook the foundations of physics, though no one realized it at the time. Everett looked at the Schrödinger equation and asked a simple, devastating question. The equation is deterministic. It evolves smoothly over time. There is no collapse mechanism in the equation itself. The collapse is something that physicists add to the math to make it fit our experience. Everett argued, why add it? Why not just accept the math as it is? If you accept the math without collapse, then the wave function never disappears. It just keeps branching. When you open Schrödinger's box, the universe doesn't choose a single state. It splits. In universe A, the cat is alive. In universe B, the cat is dead. Both are equally real. Your consciousness, your observation, doesn't collapse the wave function. It simply becomes entangled with one branch of the wave function. You are not forcing a choice. You are just walking down a specific path in a garden of infinite forks. Every time a quantum event occurs, which happens billions of times a second in every atom of your body, the universe branches. The number of universes is not just vast, it is infinite. In one universe, you married your high school sweetheart. In another, you are the CEO of a tech giant. In another, you are no longer alive. In another, dinosaurs never went extinct. Everything that can happen does happen, somewhere in the branching tree of reality. This is a terrifying and beautiful idea. It destroys the concept of a unique destiny. It implies that our choices are not really choices in the sense of selecting one future over another. We are just splitting into multiple versions of ourselves. The you reading this sentence right now is just one slice of a vast, infinite cake of existence. There is a version of you in another universe who stopped reading halfway through this sentence and went to make a cup of tea. That version of you is just as real as the one sitting here. Hugh Everett himself was shunned by the physics community. His interpretation was mocked, dismissed, and buried for decades. He grew disillusioned and left academia, working in defense contracting and struggling with depression. He died young, a tragic figure who knew he was right but was never recognized. However, in recent decades, the many worlds interpretation has gained massive traction. It is now considered one of the leading interpretations of quantum mechanics. Why? Because it is mathematically elegant. It gets rid of the messy, ad hoc assumption of wave function collapse. It treats the wave function as the only reality. In the many worlds view, the universe is not a single narrative. It is a library of infinite stories. You are not just a character in a book, you are the entire library. This brings us to a profound philosophical implication. If every possible version of you exists, does it matter what you do? Does morality matter? Does effort matter? If there is a version of you that is a saint and a version that is a monster, what is the value of your current actions? Many physicists argue that the branching only creates parallel versions. They do not interact. Your choices still define the path of your subjective consciousness. Even if other versions of you exist, you are stuck with the consequences of the branch you are currently riding. So, the stakes remain real for you. But the many worlds interpretation is just the beginning of the absurdity. Let's take the weirdness a step further. Let's move from the scale of the infinitely small to the scale of the infinitely massive. Let's talk about black holes, the monsters of the cosmos. Black holes are regions of space where gravity is so intense that not even light can escape. The classical view says that if you fall into a black hole, you are crushed out of existence. The information of your atoms, the quantum data that makes you you, is destroyed. But there is a law of quantum mechanics called the conservation of information. It states that information cannot be created or destroyed. It is the fundamental building block of reality. If information enters a black hole and is destroyed, the universe loses a piece of its reality. This is a paradox. It is called the black hole information paradox. In the 1990s, a brilliant physicist named Jacob Bekenstein and later Stephen Hawking realized that black holes are not entirely black. They emit radiation. We call it Hawking radiation. But the radiation is thermal, random. It does not carry the information of what fell inside. So, where does the information go? Enter Leonard Susskind and Gerard 't Hooft. They proposed a radical, mind-shattering solution. They argued that the information doesn't fall into the black hole. It is encoded on the surface of the black hole's event horizon, the boundary of no return. The information is stored in the fluctuations of the horizon itself. The three-dimensional object that falls into the black hole is projected as a two-dimensional hologram on the surface. This is the holographic principle. It suggests that all the information contained in a three-dimensional volume of space can be perfectly encoded on a two-dimensional surface. It is exactly like a credit card hologram. The image looks three-dimensional, but it is entirely etched on a flat piece of plastic. If this is true, then our entire three-dimensional universe, the galaxies, the stars, the planets, and you and me, might just be a projection of information stored on a distant, two-dimensional boundary of the universe. We are living in a hologram. The reality we touch and feel is not the fundamental reality. It is a low-resolution rendering of a much deeper, more complex informational structure. Think about that for a moment. The chair you are sitting on isn't really three-dimensional. It's thickness is an illusion created by the way our brains process the projected data. The separation you feel between yourself and the wall across the room is an illusion of the projection. On the fundamental boundary, you and the wall are made of the same bits of information, existing on the same flat surface. Spooky action at a distance is no longer spooky, it's just a property of the projection. The particles appear separated in our 3D hologram, but in the 2D source code, they are sitting right next to each other. It explains quantum entanglement perfectly. The holographic principle leads us to the ultimate conclusion. The universe is made of information. It is not made of matter or energy. Matter and energy are just the emergent properties of the information. If we could read the source code, we would see that reality is just a vast, interconnected network of binary choices. This is the it from bit philosophy proposed by John Wheeler. It, the physical world, arises from bit, information. If the universe is made of information, and if quantum physics shows us that the universe is discrete and probabilistic, and that observation defines reality, it looks an awful lot like a computer program. This brings us to the most controversial and terrifying question of our time. Are we living in a simulation? The simulation argument, formalized by the philosopher Nick Bostrom in 2003, is not science fiction. It is a logical syllogism based on probability. Bostrom argued that if a civilization reaches a post-human stage of technological development, a stage where they have immense computing power, they would likely run ancestor simulations. These are simulations of their own evolutionary history. They would simulate millions or billions of universes to study their own past, to run experiments, or perhaps for entertainment. If that is the case, then the number of simulated realities vastly outnumbers the one base reality. For every one real universe, there could be a billion simulated universes. Therefore, statistically, it is almost infinitely more likely that we are living in one of those simulations rather than the base reality. Elon Musk famously stated, "There's a 1,000,000,000 to 1 chance we're living in base reality." He argued that civilization's trajectory is to create immersive, indistinguishable simulations. Given that we are already making crude VR, it is inevitable. Let's look at the evidence that might support the simulation hypothesis. Consider the speed of light. It is the cosmic speed limit. Nothing can go faster. In a computer simulation, this would be the processing speed of the universe. It is the maximum tick rate of the simulation's CPU. Consider quantum uncertainty. The Heisenberg Uncertainty Principle states that we cannot know both the position and momentum of a particle perfectly. In a simulation, this is the render distance, or the optimization setting. To save computing power, the simulation doesn't render the exact details of a particle until it is observed. It uses fuzzy probability to save memory. Consider wave function collapse. When we look at a particle, the probability cloud snaps into a solid state. In a simulation, this is the optimization of the rendering. The code only draws the object when the player is looking at it. Furthermore, consider the Planck length. The Planck length is the smallest possible unit of space in physics. Nothing can exist at a size smaller than the Planck length. Why would the universe have a finite, granular resolution? Because it is a digital universe. It has pixels. In a simulation, space is not continuous. It is a grid. The Planck length is the size of the grid square. Even our own mathematics seems to be the language of the simulation. The universe is not just describable by math, it is math. The equations of quantum mechanics, the beautiful symmetries of particle physics, the elegant geometry of general relativity, they all point to a deeply coded structure. Max Tegmark, a physicist at MIT, has proposed the mathematical universe hypothesis. He argues that the universe is not just described by mathematics, it is mathematics. It is a mathematical structure that is conscious enough to observe itself. If we are in a simulation, what does that mean for us? Does it make us less real? If you are playing a complex video game, the characters in that game, if they were sentient, would feel their reality was entirely valid. They would eat, sleep, love, and fear. Their physics would be the rules of the game engine. Our physics are the rules of our engine. The fact that our universe is programmed does not make our suffering or our joy any less profound. The simulation is our reality. But it raises a critical ethical question. Who is running the simulation? Is it a benevolent creator? A bored teenager? A massive corporation running an experiment? We can't know. We are like fish in a tank, trying to understand the architecture of the house that contains the tank. We might never be able to see the outside. However, there is a glimmer of hope. If the universe is a simulation, it has boundaries, it has limitations. There might be glitches in the code. Some physicists look for anomalies in cosmic rays. Others look for peculiarities in the cosmic microwave background radiation, the afterglow of the Big Bang. They are looking for the pixels of the universe. If we find a preferred direction in space, an axis of evil, it might suggest the grid is aligned in a specific way, just like a computer monitor. So far, we haven't found definitive proof, but the search continues. Let us take a step back from the computational metaphors and the mathematical abstractions. Let's look at the human being. We are incredibly small. We are 1.5 meters tall, living on a pale blue dot in a backwater galaxy. And yet, we are the only known entities in the universe capable of asking these questions. We are the universe's self-aware cortex. We started this journey with the lies of classical physics. We saw the certainty of Newton shattered by the chaos of the quantum. We watched Heisenberg dissolve the particle into a probability cloud. We saw Schrödinger trap a cat in a limbo between life and death. We saw Einstein's beloved locality burned to ash by Bell's inequality. We jumped into the infinite branches of the many worlds and projected ourselves onto the event horizon of a black hole. We even asked if our reality is just code running on a cosmic hard drive. So, where does this leave us? We are faced with a stark choice. It is a fork in the road of consciousness. There is the nihilist's view. In this version, we are a random statistical anomaly in a meaningless quantum foam. The universe has no purpose. Our consciousness is a fragile accident, a brief flicker of light in an infinite void. The information that makes us us will eventually be scrambled by entropy. The simulation, if it exists, will eventually be turned off. Nothing we do will matter on a cosmic scale. It is a cold, hard, brutal truth. Then there is the mystic's view. This view suggests that everything is consciousness. The universe is not a physical machine. It is a mental construct. We are not just observers of the universe. We are the co-creators of it. Our minds are the interface through which the infinite potential of the quantum vacuum collapses into reality. This view aligns with the Copenhagen interpretation and the von Neumann-Wigner consciousness causes collapse idea. It suggests that love, fear, hope, and desire are not just chemical reactions. They are the fundamental forces that shape the cosmos. The universe exists because we are looking at it. Without the observer, the wave function is just an unmanifested ghost. Which interpretation is right? The physicist will tell you that both are just philosophical postures. The math doesn't care about our feelings. The math is indifferent to whether we feel cosmic importance or cosmic dread. The math just works. Regardless of the math, there is one undeniable truth. You are here. You are experiencing this. The sunrise is warm on your skin. The coffee is bitter and comforting. The laughter of a child is genuine. The grief of loss is crushing. These experiences are not abstractions. They are not probability clouds. They are not projections on a 2D film. They are the most real things in existence. The subjective experience, the qualia of being alive, is the only thing we can trust absolutely. Quantum physics might tell us that the atoms in our hand are just a blur of mathematical probabilities, spinning in a void. But the sensation of touch, the warmth, the pressure, the texture, is undeniable. Consciousness is the ghost in the machine, but the ghost is real. It is the only thing that is real. We do not know the answer to the ultimate question. We do not know why there is something rather than nothing. We do not know if the universe was created by a god, a programmer, a multiverse, or a random fluctuation. But the quest itself, the relentless, insatiable need to understand, is the definition of humanity. We are the universe trying to understand itself. We are the observers, the creators, and the observed, all locked in a recursive loop of self-discovery. Think about the sheer audacity of it. We are bags of mostly water and carbon, sitting on a spinning rock, hurtling through a void. And yet, we have grasped the fabric of space-time. We have computed the interactions of quarks. We have measured the age of the universe. We have looked back at the Big Bang. We have reached out and touched the quantum. We are tiny, fragile, finite creatures, but we have infinite ambition. We have poetry, philosophy, science, and love. We have built this civilization out of sheer will. That resilience, that spark of consciousness, is the miracle. The universe has no meaning except the meaning we give it. The code is unfeeling, but the players are not. The ghost in the machine has finally realized that it is a ghost. It has looked into the mirror of its own equations and realized it is made of smoke and mirrors. But it still wants to know who wrote the code. It still reaches for the stars. It still holds its children. It still dreams. We are living in the grandest mystery. We are searching for the holographic God. But perhaps the God is not behind the hologram. Perhaps the God is the hologram. Perhaps we are the gods, dreaming ourselves into existence, moment by moment, observation by observation. The past is a memory, the future is a possibility, and the present is the only point where the wave function collapses into reality. I am the narrator, and this has been a night tale. We have traveled from the atom to the black hole. We have danced with ghosts and stared into the abyss. Remember, at the end of the day, reality is just a word for a dream we haven't woken up from yet. The machine is humming. The stars are still burning. The uncertainty remains. And that is the most beautiful thing about it. If we knew the answer, the story would be over. But the story isn't over. The simulation hasn't crashed. The ghost is still walking. And we are still watching.